You and I are remarkably similar. We share 99.9% of our DNA, not just with each other, but with every other human being on this planet. Yet it's that tiny 0.1% that contains the instructions to make you, and me, me. That tiny fraction also holds the keys to our individual responses to food, medicine, and our predisposition to certain diseases. For a long time, medicine overlooked these subtle differences. But now we're on the cusp of a major shift towards a more precise approach. One that takes into account the genetic differences that make each of us unique in the world. I'm Silvia Lazzaris, and this is The Science of You, a podcast series about the groundbreaking science that's changing the way we approach healthcare. Together with those who are leading the charge, we will journey from the discoveries that transformed our understanding of the human body to the innovations that promise to revolutionize treatments and medical practices. The Science of You is a Cora Media podcast, supported by the European Partnership for Personalised Medicine, coordinated by Fondazione Toscana Life Sciences, and co-funded by the European Union's Horizon Europe Research and Innovation Programme. Consider this. For 99.9% of human history, our fellow humans knew nothing about DNA. Then, on a cold morning in Cambridge on April 25, 1953, James Watson and Francis Crick huddled over a fresh copy of Nature, one of the most prestigious scientific journals in the world, scrolling to find their groundbreaking discovery published in print. With the help of Rosalind Franklin's photograph 51, the very blurry first picture of DNA, they had just unveiled DNA's structure. Two long and thin filaments, twirled around one another in a double helix that hides in every cell of every living organism. Thanks to Watson, Crick, and Franklin, humanity had just taken a monumental step toward understanding the essence of life itself. After that moment, in just one generation, we not only learned how DNA works, but also built machines capable of reading it, and eventually tools that allowed us to tweak it. By the 1990s, we knew DNA was an instructional manual, written with just 4 letters: A, T, C, and G. These letters come in pairs: A always with T, C always with G. And the order of these pairs is what tells an organism's cells to build a human, an onion, or a fly. The recipe for us humans is 3 billion letters long.
Alla fine del 2000 il progetto Human Genome Project è stato completato.
At the end of 2000, the Human Genome Project was completed, meaning we were finally able to read all the letters that make up the human genome.
This is Aureliano Stingi, a molecular biologist who studies the biology of cancer and aging. He's also a science communicator about the current frontiers in medicine. I'm introducing you to our interviewees because they will be our guides throughout this episode. They're among the best people in the world to help me, and in turn you, to make sense of how genetics is transforming medicine into a more precise science, paving the way for personalized care. But let's go back to the Human Genome Project. It was possibly the most ambitious scientific undertaking in the history of biology. By 2003, in just 13 years from starting, we had decoded all 3 billion letters of the human genome. We were finally holding the recipe book for making a human being. And we understood none of it. Interpreting the human genome is currently like participating in a conversation in a language we barely understand. We catch fragments and words here and there, but we struggle to grasp the grammatical architecture and the full meaning and nuance of a sentence. The chances of misunderstanding, like laughing at the wrong moment, are high.
Agli inizi del 2000 si considerava come DNA spazzatura.
In the early 2000s, people thought 98% of our DNA was just junk. It's like thinking a book with 100 pages only had useful information on the last 2 pages, and the rest didn't matter.
Oggi in realtà sappiamo che non è così.
But now we know that's not true. Every page has meaning and plays a role, even though we only really understand a few of them so far.
Clearly, 98% of DNA is not junk. Take lactose intolerance. Today, a simple blood test can tell you whether you're doomed to a life of dairy-free lattes and sly avoidance of cheese plates at parties. But that intolerance is not caused by a mutation in a gene, rather in the space between genes. In other words, one of the first genetic traits we linked to something tangible in our lives was right in the so-called junk DNA. The thing is, when we dismiss something as irrelevant, it's often because we haven't understood it yet. Now, sure, much of our DNA remains a mystery. But even if you don't speak a language, you can still identify patterns by comparing texts and observing the order of letters. That's precisely how scientists first approached DNA, by comparing sequences across different species. Turns out, our closest relatives are chimpanzees, sharing about 98.8% of our DNA. And maybe even more surprisingly, we share 85% of our DNA with mice and around 95% with pigs. This comparative DNA approach initially led to ancestry tests, those kits that claim to reveal where your genes came from. Maybe you've got a little bit of DNA from Africa, a sprinkle from Asia, a dash from somewhere else. But please, if you find out 4% of your DNA is Italian, don't go around claiming that you're partly Italian and that explains your love for pasta. Just don't. Another way DNA tests have shaken things up was uncovering hidden relatives. Take the weird case of the 94 people who found out that they were all half-siblings, all fathered by Dr. Donald Klein, a US fertility doctor who secretly used his own sperm on patients. DNA testing has also helped us crack cold crime cases, because it identifies each of us uniquely and sticks around long enough for detectives to finally solve cases from decades ago. But scientists always wanted to get into the really impactful stuff, the kind that could change medicine. They began tracking down mutations. Remember, DNA is all made of 4 letters, so they might find a rogue C in a spot where an A is supposed to be, and figuring out if these genetic hiccups were tied to any medical conditions. Think literally of mutations as typos in a text or bugs in a program. These tiny random changes are at the basis of evolution. And they're like mistakes in a recipe that could end up becoming a disaster or a new family classic. But sometimes, even just a couple of misplaced letters can have serious consequences for our health. And sometimes can be lethal.
It means the recipe doesn't work quite as in the same way that it normally does. And there's all sorts of ways that genes can be changed, and some it's obvious that they're going to cause a problem, and sometimes it's a lot more subtle.
Rachel Horton works as a research fellow at the University of Oxford's Centre for Personalised Medicine, specialising in clinical genetics.
So if you think about a kind of a recipe for a cake or something, you could think, oh, there's a change in this recipe that says salt instead of sugar, and that's not going to work, and it's not going to be a good cake at the end of it. But if it's something more subtle, like this cake says, it needs 3 eggs, but actually this recipe has 4. It could turn out as a bit of a runny cake, or it could turn out fine. And sometimes it's really hard to judge what sort of recipe changes are important and what aren't.
Sometimes a change helps us out. Other times it doesn't. And once in a while, something that has historically saved our lives decides to turn on us. For the first tens of thousands of years, humans scraped by on the little they could find. our bodies got so good at surviving famine that those who could stretch a seed or two into a full meal became the stars of human survival. But today we're up to our elbows in an all-you-can-eat buffet of food. And that same life-saving trait is now linked to a new struggle: obesity. So what once worked in our favor is now a reminder of just how unpredictable a gift evolution can be. Despite how illiterate we still are about DNA language, the tiny mutations that we have identified so far have already been pretty crucial.
Ad esempio, per alcune tipologie di tumore al seno è stato individuato un gene difettoso.
Let me give you a well-known example. For certain types of breast cancer, scientists have identified defective genes, BRCA1 or 2. When a patient has a mutation in these genes, we now have specific ways to reduce risk. This is just one example, but it's a clear, practical way to show how years of studying the entire human genome have led to real, concrete solutions for preventing and treating diseases.
Everyone has BRCA1 and 2 genes, and their main job is to help repair damaged DNA in our cells, ensuring everything runs smoothly. But when a mutation sneaks into one of these genes, the DNA repair process can break down, potentially leading to cancer, especially breast and ovarian cancer. So, having a mutation in BRCA1 or 2 means having a higher risk of developing these cancers, which is why genetic testing for these genes is so crucial. This is just one glimpse into the world of personalized medicine. The idea that we can now take a closer look at our own bodies to identify specific risks that we should be aware of. Beyond the BRCA mutations, there are many other similar mutations which scientists have discovered are closely related to other diseases. For example, some mutations lead to cystic fibrosis, because a faulty protein causes thick, sticky mucus to build up in vital organs like the lungs and the pancreas. Certain types of Alzheimer's disease are linked to mutations that disrupt how the brain cleans up protein buildup, leading to the well-known symptoms of memory loss and cognitive decline. Huntington's disease is associated with mutations that cause nerve cells in the brain to break down over time. And then there's sickle cell anemia. Remember this one because we'll revisit it later. It's caused by mutations that change the shape of red blood cells, resulting in painful blockages of blood flow and possible organ failure. The possibility to know so much about genetic disorders brings us face to face with some tough questions. On the one hand, I think most of us would agree that an early diagnosis for a treatable disease is a huge advantage. For example, if I found out that I carry the mutated BRCA gene, I could speak with my doctor to decide if it's better to opt for regular mammograms or even preventive surgery to remove my breasts and the worry altogether. But what about genetic disorders with no current treatments or preventative measures? Imagine discovering you have the mutation for Huntington's disease, the one we were talking about a moment ago that causes nerve cells in the brain to break down over time. You would know that the disease will likely shorten your life significantly. Would you want to know? How would this knowledge impact your life decisions, like getting a job, buying a home, or starting a family?
Io ti do una risposta da ricercatore ottimista.
Here's how I see it as an optimistic researcher. In most cases, knowing you have a mutation can actually be helpful. It allows you to make lifestyle changes, things everyone should be doing anyway, like not smoking, drinking less, using sunscreen, staying active and keeping a healthy weight. These steps can help with prevention. Plus, you can take advantage of screenings that help catch problems early. For people with genetic syndromes like BRCA, there are more frequent screenings, so if a tumor does develop, it's likely to be found sooner than in the general population. Of course, it's not a great situation. I'm not saying people with these mutations are lucky. But knowing your genetic makeup at least gives you the chance to act early. When it comes to neurodegenerative diseases like Alzheimer's, where there aren't any cures, the benefit of knowing is smaller. In those cases, it really comes down to a personal choice of whether you want to know that risk or not.
sort of the how you've got to anticipate and support people through getting that sort of challenging information to deal with and respond to, but also be prepared for the fact that sometimes genetic tests don't always add quite the kind of the clarity that we hope for, and sometimes things are a bit you're still left with uncertainty at the end of the test, just sometimes different sorts of uncertainties. In my clinical work that I've done, I've frequently offered genetic or genomic tests to people, and sometimes they're extremely helpful and the results of them make a profound difference to people and families. Often there's not necessarily a treatment, for example, if you identify a rare genetic condition in a child, but just having that sort of detail as to what the diagnosis might be lets people find other families going through the same thing, take part in research that can hopefully one day move things forward so treatments might be possible, gives people some clarity as to what to expect for the future. Not always, but sometimes there'll be adults known to have the condition, and you can see kind of what's happened for them, and it also gives people some clarity about what the chances might be if they were to have another child. Would they be affected by the same genetic condition or not?
That's why, as patients, we have a right not to know. But I also find comfort in the thought that, as our abilities to diagnose genetic disorders advance, so too must our capacity to treat them. And we are getting there. Because another discovery has been in the making since the 1980s. Halfway around the globe, in Japan. In 1987, Japanese scientists led by Yoshizumi Ishino were immersed in the study of Escherichia coli, the bacterium infamous for making us regret ever drinking that questionable glass of water. In their quest, they stumbled upon a bizarre discovery. Strange DNA sequences in the genome of the bacterium, repeating themselves at regular intervals. They named these sequences CRISPR, clustered, regularly interspaced, short palindromic repeats. Not exactly a catchy name, but it got the job done. While these scientists were still scratching their heads, molecular biologist Francisco Mojica, in Spain, was having what might be called a eureka moment of his own. Mojica proposed that bacteria were using these CRISPR sequences like a wanted poster. Bacteria, it turns out, often engage in battles with viruses. And so Mojica proposed that bacteria were storing fragments of viral DNA to remember an old enemy. A way to recognize and attack any virus that dared to show up again. He turned out to be right. CRISPR was a bacterium's immune system. What was still unclear was how the bacteria managed to track down those specific sequences in the genome of their nemesis. The answer came when in 2007, Philip Horvath, a French scientist working for Danisco, a Danish food company, was examining the bacteria in yogurt and observed that the bacteria were using proteins to fend off the viruses involved in yogurt production. In simpler words, it was as if CRISPR were the brain, and these proteins, soon dubbed Cas9, were its loyal attack dogs, tasked with the dirty work of slicing up viral DNA on command. Then, in a moment that must have felt like a cosmic high five, Emmanuelle Charpentier and Jennifer Doudna, in 2011, found the missing piece. They discovered that Cas9 proteins were guided by a little tool, like a GPS system that they called trans-encoded RNA, which directed these proteins precisely to their DNA targets. Bacteria had just provided us with a compass and a scissor to slice specific pieces of DNA. Any piece we could ever want. Charpentier and Doudna, with this revelation, not only helped science make a giant leap forward, but also won a Nobel Prize. Thanks to their breakthrough, the medical world could now envision editing genes, changing specifically faulty bits of DNA, and perhaps freeing us from genetic diseases altogether. This year, 2024, will go down for many terrible events. But also as the year when we started curing sickle cell disease with gene editing. You might recall sickle cell from earlier. It's the condition where red blood cells end up shaped differently, causing immense pain and a life expectancy of about 53 years. The culprit are two genetic mutations affecting hemoglobin, the protein responsible for carrying oxygen through our blood. These mutations cause the red cells to become misshapen, blocking blood flow and leading to severe complications. But scientists have realized that our bodies have a backup plan for making hemoglobin that becomes dormant when we're born. A simple DNA edit to cells from the bone marrow could switch this engine back on. In 2022, Vertex Pharmaceuticals, based in Boston, was the first to ask for the green light from regulators in the UK and the US, and to get it. The results? Almost all of the trial participants were suddenly pain-free. Jimmy Olaguier, one of the first to undergo this therapy, reported feeling like he'd been given a wholly new life. His energy levels soared. He could recover from exhaustion with just a good night's sleep, like most of us. And he felt ready to be present for his newborn child. His symptoms didn't just improve. They seemed to vanish overnight. There's a small issue, though. The cost of this gene editing treatment is a staggering $2 to $3 million. And where is sickle cell disease most prevalent and most deadly? Africa, where as of 2019, 85% of the population lived on less than $5.50 a day. The price reflects the complexity of the treatment, which involves a meticulous and long process. Doctors extract cells from a patient, edit them, and then reintroduce them into their body. The procedure can be grueling, often requiring months from start to finish. And sometimes even preventive chemotherapy is needed. Jimmy Olaguier, for example, spent 17 weeks in the hospital. While his personal outcome was profoundly life-changing, he expressed disappointment that the companies behind this breakthrough hadn't sufficiently considered its exorbitant cost, creating a stark disparity between those who can afford the treatment and those who can't.
CRISPR-Cas9 is super powerful and effective, but right now, its use is still pretty limited. The more we learn about how our genetic code works and how our bodies function, the more we'll be able to use CRISPR. But there's a catch. It's a systemic therapy, meaning it changes DNA in all cells. So we need to know not just which DNA sequence is faulty, but also which specific cells or tissues are affected. For example, if I have a faulty gene in my liver, I need to target the liver. It's complicated now, but CRISPR is precise and powerful. I'm sure we'll see it being used more and more in the future.
We're a long way from using CRISPR-Cas9 to solve all our problems. And it's wise to temper our enthusiasm, because there's still a mountain of hurdles to overcome before these treatments are within reach for the majority of us. But let's not forget, CRISPR is not the only development spurred by our understanding of DNA. Let's shift our focus to cancer. Now, contrary to what you might expect, few cancers have a clear genetic explanation.
Si stima che siano 10, massimo 15% dei tumori.
It's estimated that only 10 to 15% of cancers are genetic. The rest, according to the World Health Organization, develop due to environmental factors. And here's probably the most important fact you'll hear today. Around 1 in 2 cancers can be prevented through lifestyle choices.
But we should remember that there's not just our DNA. Cancer cells have their own version of our DNA. Cancer begins when healthy cells make mistakes while copying themselves for routine renewal. Remember that our bodies replace around 330 billion cells every day. And sometimes those mistakes lead cells to replicate uncontrollably, and their growth goes undetected by our immune system. This faulty cancer DNA is now at the heart of early cancer detection. A new technique called next-generation sequencing can spot tiny traces of cancer DNA that shed into our bloodstreams. Why does this matter? Because it can allow us to detect cancer early without needing invasive biopsies. Plus, even small amounts of cancer DNA could signal a relapse or a metastasis, and this way we could catch them more easily. Next-generation sequencing can also map the genetic makeup of tumors, tracking down mutations that might tell us if the cancer is still active, and helping doctors to target the cancer directly with treatment, instead of relying on one-size-fits-all treatments like chemotherapy, which can be debilitating for the whole body. Once doctors have the genetic profile of a tumor, they can match it with existing specific treatments designed to take it down. For example, in breast cancer cases caused by the BRCA1 gene, doctors might use some drugs called PARP inhibitors, which exploit the weaknesses in the DNA of the tumor to trigger self-destruction. But let's not get too carried away just yet. There will still be a bit of a way before these tailored treatments are available to everyone. What is now certain, though, is that this time will come.
Penso che la prevenzione sia veramente la chiave.
I really believe that prevention is key in oncology. Prevention is something we need to focus on every day through healthy lifestyle choices. We all know the recommendations. From a research perspective, I think the real breakthroughs in the future will come from understanding why certain cancers develop and which gene combinations lead to cancer, rather than just creating new drugs to treat it. I just think we'll have more success preventing cancer from forming than treating it once it's already there.
For half a century now, our societies have experienced bouts of enthusiastic frenzy about genetics, convinced that once we cracked the genetic code, we'd magically be able to predict, prevent, and cure diseases with surgical precision. And don't get me wrong, our understanding of the genome has taught us an incredible amount about our bodies and diseases. Medicine is quietly becoming more powerful and precise. But if we thought that the handbook to make a human would also give us all the answers on how to keep one alive, well, things, as it turns out, are a bit more complicated than that.
These brilliant stories are representative of the hope, but not of what's actually happening for the bulk of people having these tests. And more often it's sort of like, oh, yeah, sorry, we didn't find anything, or oh, we found this and we're not quite sure what it means, but we'll see you again in 5 years and see it. Maybe we can tell you more then. If the language around genetics is always about the sort of shiny and exciting aspects, then people who are having tests which don't lead to that, I think, are not as well prepared for getting that. And I think there's also challenges when we move into things like newborn screening or direct consumer tests. If all the language around genetics is about how powerful it is, what it'll tell you, the clarity it'll bring you, then if you happen to be one of the people who has a different experience from those tests, it's sort of even harder because you've not been prepared for it by the way that genetics is talked about and by the expectations we bring to it. We had this sort of welcome to medical lecture, and it's saying kind of in 10 years' time, you'll go to your GP, they'll have your genome to inform their prescribing, and that still hasn't happened.
That's because conditions and diseases are not just a matter of faulty genes. They're also influenced by a whole host of other factors, other molecules in our bodies, our environments, our lifestyles, and the intricate dance between our genes and these external elements. It's like trying to fix a car by just focusing on the engine, while the tires are bald and the brakes are shot.
Oggi abbiamo altri elementi,
So, there's another layer of complexity that helps us understand why two people with identical genetic makeup, like identical twins, can have different health outcomes. For example, we have the microbiota, which is a community of living organisms that resides in and on our bodies, and it significantly influences how our bodies function. Plus, there are thousands, if not billions, of molecules and substances in our bodies and environment element that can interfere with and regulate our health. The complexity is immense, as you can see. But the good news is that today we have all these elements on the table, and we can start combining them to gain a better understanding.
The promise of genetics is enormous, and now more than ever, within reach. It's hard to overstate how the discovery of DNA and genome sequencing shifted the entire framework of medicine. Suddenly, the idea that one treatment could work, or work the same way, for everyone felt, well, quaint. We began to see that the difference between our bodies, their quirks, their vulnerabilities, were not just important, but crucial to understand how to diagnose, treat, and prevent disease. Take Abacvir, for example. It's an HIV medication that for about 5% of patients once triggered a severe allergic reaction. As it turns out, that reaction was tied to a single gene. And once scientists figured this out, they began testing patients for the gene before prescribing the drug. Severe reactions nearly vanished. This is the kind of future that is quietly unfolding around us. One where medicine becomes more tailored to the needs of an individual body. At the same time, what genetics has taught us is humbling. Every time we think we've cracked the code to a healthy life, another layer reveals itself. That's why personalized medicine today isn't just about finding genetic mutations. It's about peeling back all the layers. In the coming episodes, we'll dive into those layers and explore how they're shaping the future of healthcare. The Science of You is a Cora Media podcast, supported by the European Partnership for Personalised Medicine, coordinated by Fondazione Toscana Life Sciences, and co-funded by the European Union's Horizon Europe Research and Innovation Programme. The podcast is written and hosted by me, Silvia Lazzaris, with editorial support from Simone Clemente and editorial curation by Graziano Nani. Sound and music supervision is by Luca Micheli. Post-production and editing are done by Andrea Girelli. The sound engineer is Luca Possi. The project manager is Silvia Arcidiacono Mutti. The producer is Martina Conte, with post-production coordination by Matteo Scelsa. Thanks to Francesco Zaffarano for his voiceover.